In this video, we'll explore a new kind of test for regression coefficients, an F-test. Throughout, we'll use data on 100 restaurants to explore the relationship of a restaurant's average rating from 0 to 100 with various characteristics. First, we have a set of 0 to 100 ratings on the restaurant's decor, lighting, appetizers, entrees, desserts, and drinks. Further, we have data on the restaurant's cuisine type. Notice then that 2 features here are related to ambiance, and all of the others are related to food. Now let's test various hypotheses about these features using a 0.05 significance level throughout. To begin, let's model restaurant overall ratings by how well it scores in the ambiance-related features, decor and lighting. We can fit this relationship by applying the LM function to our restaurant's data. Notice that decor and lighting both have positive coefficients, suggesting that restaurant ratings are positively associated with both features when adjusting for the other. But are these associations statistically significant? Consider the decor coefficient. Recall that we can use the information in this row to perform a t-test on the beta 1 decor coefficient, the null hypothesis being that this coefficient is 0, and the alternative being that it's non-zero. With a p-value of roughly 0.097, we can conclude that when adjusting for lighting, we do not have statistically significant evidence of a relationship between rating and decor. We can test a similar hypothesis about the lighting coefficient. Here, too, the relatively high p-value of 0.187 means that, when adjusting for decor, we do not have statistically significant evidence of a relationship between rating and lighting. These results might seem surprising. Going back to the raw data behind this model, the plot here, with each dot representing a restaurant, suggests that ratings do increase with decor and lighting. This is a reminder that we have to be cautious in our hypothesis testing interpretations. Mainly, the t-test suggests that there is not sufficient evidence of a relationship of rating with either decor or lighting when adjusting for the other. This does not mean that rating isn't related to decor and or lighting. Again, our plot suggests that it probably is. All to say, we need another type of test that doesn't just test one individual coefficient at a time. In fact, revisiting our model summary table, another test has been there all along. Specifically, the last row of this output provides information about some test statistic and a corresponding p-value. It turns out that this information corresponds to an F-test, whereas the t-test evaluates the null hypothesis that a single coefficient is 0, the F-test evaluates the null hypothesis that all of the non-intercept coefficients are 0. The alternative to both coefficients being 0 is that at least one of them is non-zero. Though this is a different type of hypothesis test than we're used to, we can use the p-value of 0.0004 the same way as we do in the t-test to evaluate the consistency of our data with the null hypothesis. Thus, the small p-value here suggests that the trends in our data would be very unlikely if in fact restaurant ratings are unrelated to both decor and lighting. That is to say, we have evidence that there's at least some relationship of rating with decor and or lighting. Putting these together, the t-tests indicate that, at least loosely speaking, lighting doesn't tell us much about rating that's not already explained by decor, and decor doesn't tell us much about rating that's not already explained by lighting. But the F-test clarifies that at least one of decor and or lighting tell us something about rating. Though these conclusions might feel contradictory, they're not. It's important to remember that the t-tests and F-tests are evaluating different hypotheses, and both of their conclusions can be true here. Mainly, as captured by the F-test, rating is indeed associated with decor and with lighting. But since decor and lighting are also strongly associated with one another, as demonstrated by the highlighted plot here, one doesn't tell us much on top of the other, hence the results of our t-tests. Mainly if I have one of these predictors already in my model, the other one might not add extra information about rating. There's more to learn ahead, but let's summarize what we've covered so far. The summary output of a regression model includes information about two types of tests. First, t-tests evaluate whether specific individual coefficients are 0 versus non-zero. Thus, a t-test essentially compares two models. Model 1, the original model including all coefficients, versus Model 2, which is the same as Model 1 but drops a single coefficient and its corresponding covariate. In comparing these two models, we say that Model 2 is nested within Model 1. It doesn't contain any covariates that aren't also included in Model 1. It's inside that model. Our model summary tables also report an f-test that evaluates whether all non-intercept coefficients are 0. This also boils down to the comparison of two models. Model 1, the model with everything, and Model 2, a very simple model with nothing but an intercept term. And again, Model 2 is nested inside Model 1. Mainly, it contains no non-intercept terms, so it doesn't contain anything beyond what's also in Model 1. Okay, so we can do a t-test for one coefficient or an f-test for all coefficients, but sometimes we're interested in testing hypotheses between these two extremes about some coefficients, where by some I mean more than one, but not all. Consider a model of a restaurant's overall ratings by its ratings on various features, both some related to food in orange, and some related to ambiance in blue. Now, instead of evaluating one feature at a time with t-tests, or all of the features at once with an f-test, we might want to evaluate a themed subset of these features. For example, suppose we wish to explore whether there's a relationship between rating and the collection of ambiance covariates, decor and lighting, when adjusting for the food factors. That is, we want to compare this big model to a smaller but still nested model that drops the decor and lighting coefficients. In mathematical notation, we want to test the null hypothesis that the decor and lighting coefficients are both equal to 0 versus the alternative that at least one of the coefficients is non-zero. In fact, just as when we tested the full collection of model coefficients, we can evaluate these hypotheses using an f-test. But there's a but. When we fit the big model here, the summary output only includes t-tests for the individual coefficients and an f-test for all coefficients. Nothing here tells us about the subset of ambiance coefficients combined. So we need some new R code. First, we need to fit two big models. Our original big model that includes all covariates of interest and the still big but smaller nested model that removes the decor and lighting terms. We can then compare these two models using the ANOVA function. Notice that we supply this function with two pieces of information. First, the smaller model, and second, the bigger model to which we're comparing it. And the order here is important. Small model, big model. And the last row and column highlighted here contains the p-value for our hypothesis test. Given how large this p-value is, when adjusting for food rating, we do not have evidence of a relationship between rating and ambiance ratings. That is, we don't have evidence of a relationship between how well a restaurant scores overall and its decor and lighting in particular. Or loosely speaking, ambiance doesn't tell us much about restaurant ratings on top of what's already explained by the food-related covariates. For extra practice, let's evaluate the null hypothesis that the food-related coefficients, beta 1, beta 2, beta 3, and beta 4, are all 0 versus the alternative that at least one of them is non-zero. That is, we want to compare the big model with all ambiance and food-related covariates to a smaller one that drops the food-related covariates. Again, since this hypothesis goes beyond testing a single coefficient, but not as far as testing all coefficients, we need to fit both models here, and then compare them using the ANOVA function, small and then big model. The small p-value in the ANOVA table here indicates that we can reject the null hypothesis. Thus, when adjusting for ambiance ratings, we do have statistically significant evidence of a relationship between a restaurant's overall ratings and its food ratings. Or loosely speaking, these food covariates contain unique information about restaurant ratings that's not already accounted for by ambiance. Finally, let's consider another common and powerful application of the F-test, testing hypotheses about categorical covariates. For example, consider the model of restaurant rating by lighting and cuisine type, where cuisine falls into 3 categories: pizza, ramen, and tacos. By default, since pizza is the first alphabetically, it serves as a reference category for this model, thus does not appear in the list of our coefficients. We have to be mindful of this fact when interpreting the Raman coefficient and corresponding t-test. First, the negative coefficient here suggests that when adjusting for lighting, ratings are lower for ramen restaurants than for pizza restaurants on average. However, the relatively high p-value for the t-test indicates that this difference is not statistically significant. That is, when adjusting for lighting, we do not have evidence of a difference between the ratings of ramen versus pizza restaurants. Similarly, though the positive taco coefficients suggest that ratings are higher for taco restaurants than for pizza restaurants when adjusting for lighting, the high p-value indicates that this difference is not statistically significant. Okay, so thus far we understand that restaurant ratings for ramen and taco restaurants don't significantly differ from pizza restaurants. But comparing other cuisine types to pizza because pizza comes first in the alphabet feels pretty arbitrary. What we really want to understand is whether or not restaurant ratings are related to cuisine type overall, combining all cuisines. So again, this question boils down to asking if we can drop the cuisine covariate, hence the corresponding ramen and taco coefficients from our model. Thus, we can perform an F-test of the null hypothesis that beta 2 and beta 3 are both 0. To this end, if we fit the big model with both lighting and cuisine type and the smaller model with only lighting, and then compare them with the ANOVA function, we get an answer to our question. The resulting small p-value suggests that we can reject the null hypothesis and conclude that yes, we do have statistically significant evidence that there's a relationship between restaurant rating and cuisine type when adjusting for lighting. Bringing together our cuisine observations, the t-tests indicate that when adjusting for lighting, ratings aren't significantly different for ramen versus pizza restaurants, and they're not significantly different for taco versus pizza restaurants. But the F-test clarifies that cuisine type is related to rating when adjusting for lighting. To understand how both can be true, the plot of ratings by cuisine types offers some insights. First, notice that ramen and taco ratings do not appear dramatically different than pizza ratings. That is, the pizza box plot overlaps quite a bit with the ramen box plot, and it overlaps quite a bit with the taco box plot. But ramen and taco ratings do appear different from one another. Mainly, taco restaurants appear to have significantly higher ratings than ramen restaurants. To conclude, we've explored 3 types of tests in this video. The first is the more familiar t-test, the purpose of which is to test whether a specific individual coefficient is 0. In R, we perform this test by fitting the model of interest, obtaining a model summary, and checking out the corresponding row in the summary table of coefficients. Next, we can use an F-test to test whether all non-intercept coefficients are 0. In R, we perform this by fitting the model of interest, obtaining a model summary, and examining the last line of the summary output. In between these two extremes, we can perform another type of f-test, which evaluates whether some coefficients are zero. In this case, in R, we must fit two models, the bigger one, which includes all original covariates, and the smaller one, which drops the coefficients or covariates of interest. We can then compare these models using the ANOVA function. And what I also hope you gathered from the examples in this video is that different tests provide insights into different hypotheses. And these different angles provide a more complete picture together than any one test can provide alone.